This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Low speed means if you use for data communication, suppose your data rate is very high, for DC it is fine. You want to isolate analog DC part, digital DC part, or some different part of the DC part, optocoupler is the best solution. But optocoupler can also use it to isolate the signals. Then what signals? If the frequency of the signal or data, if the data rate is very high or the frequency of the signal is very high, then not good. Low speed only it can be used. High speed switching for LED is difficult. That's the reason. Then power hungry, low volt operation with degraded performance. Drive current performance degradation over lifetime. So over the lifetime, the performance will decrease. Then you also got a magnetic inductive transformer or GMR, giant magnetic ratio. So transformer or inductive. New technology approved by industry leaders. Low power over optos. Inherent low immunity to electromagnetic noise. No ESD protection. Then data integrity issues at power up, power down. So these are the features of magnetic. Then capacitive, high immunity to electromagnetic noise, low voltage operation, power lower than opto but higher than inductive. So because you are using an isolation techniques, but then that techniques itself need power. You turn it on, your that isolation IC. So that is more, optocoupler need more.
Excuse me, with the capacitive, if it lets AC current through, is that galvanically isolated?
No, capacitor is again just simple capacitor is not a galvanic isolation, because simple capacitor means you are connecting a capacitor, then your signal, but then not galvanic isolation. But there are some ICs they designed with the capacitor as isolation, but then here they will be using some different technique. Yeah. Answer to your question is, if you use a simple capacitor, that will not give you galvanic isolation, because that will only block your DC, but the ground you need to connect it. But if you use a clever design, some ICs are there where you will be using a galvanic, you may get a galvanic isolation. Yeah, so good question. So galvanic isolation means is the capacitor. This question is important, because if you are using a capacitor for the isolation, you want to isolate the DC. And then maybe this question is a good question to explain the galvanic isolation. So his question was, can we use a capacitor, simple capacitor for isolation? Because here you got plus 5 digital, here you got plus 5 analog. Then if you are using a capacitor, what is happening is the capacitor will block the DC. But then the problem is the ground you have to share it again. But then galvanic means both the supply rail and ground should be isolated. So that's called galvanic isolation. So so comparing isolation solutions, noise immunity. So if you are looking for noise immunity, bad, magnetic is bad, good, capacitive and optical are good, because that is noise immunity. Obviously magnetic things are always immune to noise. Power transfer, if you want to transfer the power, what do you mean by power? Because you want to transfer some current from one side to other side, but same time you want to isolate the both power rail and ground. In that case, how will you transfer the power? Somebody will ask, can you transfer the power? What you will be transferring? Your current in the isolation, because you are transferring the current. So optical, why optical is bad? Because the LED light is anyway small. So the photodetect is detecting, and then you are using a transistor to amplify. You can't transfer big current. So hence the power. Good, capacitive is okay. Magnetic is excellent. So that's the reason when you transfer the power. So this is your wireless charging. Still magnetic is the best, because you can charge it. Though other techniques are there, still this one is quick. Age degradation. Bad, optical is not good, it will degrade quickly. Capacity and magnetic may got more lifetime. Then this isolation ICs are an emerging area. Lots of research is happening in the isolation. And then in the isolation, now we understood how isolation works. Somebody understood, you got LED, you got a photodiode then connected to a transistor, or a light sensitive transistor, and then the signal is going through. So that is giving you an isolation. Then some other people thought maybe we can design a better isolator. So they designed SI84110 isolator. So this is called a low power single and dual channel digital isolators. So they can get high speed operation DC to 150 megabits per second. No startup initialization required. Wide operating supply voltage 2.7 to 5.5 volt. And then this, how this is working, how they can get low power single and dual channel digital isolate. So this is a different design. Here what they are doing is the following. So they have got your signal is coming, then you are modulating, then you got RF oscillator. See the complexity, and then semiconductor based isolation barrier. So here you got some semiconductor material, this is the barrier. Then you got demodulator, then you are demodulator, then you are recovering the signal. The operation of SI84XX channel is analogous to of an optocoupler, except an RF carrier is modulated instead of light. See, previously you used LED, that's how people would be thinking, that's how you should be thinking, that's the reason I have included this slide. So until some time there was only the LED, so you got the LED. So that's the reason thinking differently is important. Previously what happened is you got LED, and then this is a name, sorry, LED. So in the optical isolator, so LED is shining, maybe a photodetector, and then that is connected to a transistor, and so you are getting the collector current here. So that's how, so this LED, the current, the light is going, and then you are getting some base current, you are getting the collector current, and then this both part are isolated. But then people started thinking, maybe can we use RF instead of optical within the chip? So that was the first question they thought. So that's the reason we have to be constantly thinking when we see some technology. That's how people are coming up with new ideas. So these guys thought about RF. So due to an optocoupler, except RF carrier is modulated instead of light. Transmitter modulates the carrier provided by a RF oscillator using on-off keying. Receiver, this is a receiver, contains a demodulator that decodes the input state according to its RF energy content and applies the result to output B via output driver. I will show you the diagram. See, on-off keying, what do you mean by on-off keying? On-off keying is the simplest form of amplitude shift keying modulation that represents digital data as the presence or absence of carrier wave. Means logic on-off keying means OK. So what means when you light on 1, logic 0, light off, light on 1, light off, something like that. There is no modulation technique. See, logic 1, 2 volt, logic 0, 0 volt. That is called on-off keying. Then what they do is they got a carrier frequency, and then here, so this one is called here they are doing, see, if you are, this is your signal, and then modulating frequency is this is a carrier signal. If you are doing frequency modulation, what will happen is logic 1, it is signal frequency is there, this part frequency is not there. But then on-off keying, this is the input signal, and then what will happen? So your modulation means here you are getting signal, but here you don't get any signal because this is a logic 0. Here again you are getting the carrier, here you don't get the carrier. And then something like here also the same thing happening. See, here you are getting a little bit here. But if you are doing a frequency modulation, what will happen is this area will have more frequency, this area will have low frequency. You know what I mean? Frequency modulation. But then here it is not frequency modulation. Here we are using on-off keying. In the on-off keying, what is happening is when you have logic 1, then you got the signal. And then here logic 0, then you don't have any signal. And then that's the reason here your output frequency, see, you don't have anything, then again you are getting the frequency. So when you take 1 0 1 0, then you will be seeing like this, something like this, and then this is what it is sent through, and then it is the recovered one. So recovered one, so this is the transmitted one, and then this is the received one. So this will be transmitted, this is your input signal, and then this part is transmitted, and then this will be received, and then from this one you will recover the output signal. See here, so here from here what you are going, here what is going out is something like this signal, and then here it will receive it.
May I ask why the capacitive can immute noise? Because I think that if we can transmit the high frequency signal, I think that the noise bandwidth is also higher.
Yeah, capacitive got the noise problem. Capacitive got not only noise problem, when your frequency is increasing, you may have parasitic components. But then these isolation techniques are not suitable in the gigahertz, that range, high frequency. Usually people use in the megabits per second, that regime. There are some isolation, but that is not based on the capacitor. So if you want to make a very high speed one, what will you do? That's the reason RF. See this one, why people, then you might be thinking, why these guys are crazy, they are replacing LED with RF. Why they want to complicate? Because when you have RF, you can increase the frequency if you got signal. So their advantage is they can isolate it from DC to RF, DC to very high frequency. So that is isolation also is an emerging area in research, because the problem is how will you isolate? DC isolation is okay, but then when it comes to signal, the problem is depending upon the frequency, it is challenging. Like you have to ask the capacitor is, then you have parasitic inductance when the frequency increases. Then so this one RF means you can increase the data rate, and then same time you can get the isolation. Then RF also, when you design, you should make sure that it is confined in that small region, because otherwise the RF will interfere with other circuits. So you need a proper isolation when you are making these type devices. Yeah, so that's all about isolation techniques, and then I will be discussing about, anyway we got the time, the communication protocols. So the DSO, which communication protocol you are using? Yeah, so what is SPI? People might ask. So what is the expansion for SPI? Serial to parallel. No, it's not parallel. Serial peripheral interface. Then what is UART? Because the name also, from the name itself you can get some idea about how it works. So UART means there is an asynchronous. Yeah, so there is an asynchronous. And then you got I2C, some people say I square C, I2C, so up to you, I2C. And then you also got TXRX. So maybe we'll be discuss about a little bit, because we got time. So embedded communication protocols comparison. So I will upload these slides on LMS. So first one is SPI, serial peripheral interface. And then what is SPI? So in the SPI, you got a master, SPI master. It may be microcontroller that is interfacing with maybe SD card, maybe a clock or something else. So this is called SPI. When you SPI means before going to the application, SPI, serial peripheral interface. It has 3 wires plus 1 chip select. So 3 wires means when you have a master will be a microcontroller. Then you are connecting to maybe 3 different places. One may be some sensor, and then this may be a SD card. This may be a display. So you can connect your microcontroller to display, SD card. Maybe you are doing something else here. And then when you have 3 wires plus 1 chip select, why do you need a chip select? Chip select means this SPI, the microcontroller, I call it as master. Master has to tell to where it is communicating, to SD card, or because it is connecting to these three sections. SD card, maybe this is a display, this may be something else, your sensor or something, then it has to tell which one this one is communicating. So that's the reason it got a one chip select. So 3 wires plus 1 chip select for every slave. See. Then MOSI, so master out slave in. So this is a master out slave in. See, this one is going here. MISO, master in slave out. So master out slave in means, see, it is going from the master, it is going to the slave. It is going to the slave. So master out, coming out of the master. Then master in slave out means it is going from slave to the master, maybe from your SD card back to your microcontroller. So microcontroller is a master when you are using SPI. Then SCK means that is a clock. There is a clock. So it is a synchronous. So whenever there is a clock present, that is a synchronous. Clock is shared with all the slaves. So the clock will be shared with all the slaves. And then on every clock pulse, because there is a clock, the master sends 1 bit and the selected slave sends 1 bit, back. So that's how, that's a correct wording on every clock pulse. So slaves can only send when polled by the master. So slave cannot, communicate to the master until your microcontroller says, okay, you communicate. And can be high speed. Then what are the SPI? 80 mega 16 supports 8 megahertz with 116 megahertz crystal. So it can be high speed. And the LTC 2376 supports at 100 megahertz. See, so high speed applications, SPI is very good. So this is see, we got this diagram. So this is a master shift register, and then this is a slave. So MOSI, so master out slave in means your data will be coming like this, and then slave in, master in, slave out. So from the slave also data is going like this to the master. You know what I mean? So this is going like this. Every clock pulse, 1 bit sent from master to slave, 1 bit sent from slave to the master. So it's a two-way communication. That is SPI. And then because you use a clock, then if you want to have a more understanding, so this is a clock and then these are the clock diagrams. But then I think if you want, you can look at it, but this will explain, how it is one clock. Every clock, one data, 1 bit is coming, and then from slave 1 bit is going. Then the question is which slave? Then that master will select it. That's the reason select pin. Example. So this is what I want to show. So you got a microcontroller, then you want to measure temperature, pressure, humidity. You got some sensor. Okay. So then you want to make a portable weather station. So this is example, because this example is important. So what do you mean by portable weather station? So you got a sensor. That sensor can measure temperature, pressure and humidity. And then your application is you want to measure those values, and then you want to store it in SD card. Then also you want to display on LCD. So you want to make a portable weather station. Then you can use SPI. Because you got a microcontroller, then this SPI means here you already got 3 wires. So I have drawn only like a thick wire, means here already got 3 wires. Then these are the control ones. Then you will be connecting like this. Means microcontroller, so that is your master. These are the slaves. And then here these 3 lines are going here, 3 lines are going here, 3 lines are going here, because these 3 lines, you see here 1, 2, 3 lines. And then that is the 3 lines I have shown as a thick line, and then this is a select one. Which one should be selecting? So need a device that can measure temperature, pressure and humidity, display these readings on an LCD and log on to an SD card. You also want to log on, not only displaying. Then SPI is used as there are reasonably small number of devices that need to be connected to the microcontroller. So this you got only one sensor, one SD card, one LCD. So you can use the SPI. SD cards can be accessed directly using SPI without the need of extra hardware. SPI is also fast enough that LCD can be updated quickly without noticeable lag. So here you are connecting only limited number of devices, SPI, limited number. Always remember limited number. So if you have got so many sensors, you can't use SPI. So that is a SPI we cannot use when you have so many. So when you have so many devices, for example, you got 10 sensors or 20 sensors. You are reading and then you are dealing with the 20 sensors. But then you are using a microcontroller, you can't use SPI. So if you got more devices, then you have to go for not SPI, you have to go for I2C. So people might ask I2C. But then I2C, I will come to how people thought about I2C, because SPI, please understand, from microcontroller you got 3 lines. 3 lines are going to each slave. Means your sensor 3 lines, SD card 3 lines, LCD 3 lines, and then you can select, microcontroller can select which one it is communicating. So that you know what I mean by 3 is going here, 3 is going here, 3 is going here, and then you are selecting which one. So that is the SPI. Then before going to I2C, maybe you should UART. So universal asynchronous receiver transmitter. So that's a UART. So 2 wires, very simple, TX and RX. Only supports direct device to device connections. So this is the device 1, device 2. So this RX, TX. So RX means receiver, TX means is transmitting. Asynchronous, see, from the name itself, asynchronous. Why it is asynchronous? Because there is no clock. And then speed must be set on both sides, and clock is synchronized using start bits. Then how can we synchronize the clock? Because you are communicating from here, you are receiving here. When you have SPI, the advantage is it is synchronized. Without synchronization, how can you send the data from this side to this side? You know what I meant? When you send data, then you are using a clock here. If you use a different clock here, you can't process it. So then in the SPI, there was no problem with the synchronization because you are transmitting the clock. But then here, what they do is, because there is no clock, what they do is when a bit is, one bit is sending, and then the clock is synchronized during the start bit. When the start bit is going, then both are synchronized. They will say that, okay, start the clock. And either or both devices can send data at any time. No need of polling. Like you don't need that kind of selection. Maximum speed generally 250 kilo bits per second. 80 mega 16 supports 2 Mbps with 16 megahertz crystal. So UART, so another type of communication, and it has got only 2 wires, simple, but it is asynchronous. And the start bit, when the TX is sending some data from here to here, the start bit, then the clock will be synchronized. And then UART protocol. So UART frame diagram, since the communication is asynchronous, all settings must be entered on both the devices. So that is one thing. A low start bit is used to synchronize the transmitter and receiver, because you need a bit that will synchronize both the receiver and transmitter. Then 1 to 9 data bits can be transmitted, usually 8. An odd or even parity bit can be included after data bits. 1 or 2 high stop bits are used to signal end of the frame. So because when you say this is end of the data, you have to say that's end of the frame. Line is held high when idle. Then, so this is a kind of a UART. There will be a start bit, then the synchronization starts, then the data will be transmitted, then there will be a stop bit. So that's the UART works. Then, without understanding how exactly SPI works, UART work, you can use these things, connect it. You got a UART communication, some coding. It will work, communicate, but you should know how it is communicating. Why? Because if you don't know how it is communicating, you won't be able to figure out some issues in your device when you have communication. I have seen in capstones some of the interfacing failed because that communication scheme was not suitable. They said that, oh, my communication scheme failed. An example is somebody was interfacing a couple of sensors using I2C, using microcontroller. But then when you are using I2C, the problem is it should have different addresses, because it's got same address, because that is one of the common issue I see when you interface it, because some of you are laughing because they are doing capstone with me. Yeah, so if you got different addresses, then you will have this issue. But then you can get rid of it by using a max or something. Then you can get rid of this issue. Anyway, I'll come to I2C, then I can discuss. So UART, so this is a UART. But then also you can think of, if you want to develop some new protocol, you can think of it. But if you don't know how these things are working, how can you find out a new one? When you find out the new one, that may be the I2C. So that's the reason you should know. So these are the UART. Then maybe the next one is Yeah, UART example. So where you are using, so Raspberry Pi debug interface. That's the best example of UART. Need to access a Raspberry Pi without networking and without connecting a screen and keyboard. UART is used since it removes the need of constantly polling. At any point in the time, the user might send a keyboard strokes to the Raspberry Pi, or the Pi might send data to the computer. See, UART, we can, a simple one, Pi you want to connect to the computer, UART. UART allows for this to happen without any polling delays. It's very, very simple. Next comes I2C. So what is I2C? Integrated circuit. So integrated circuit was developed as a trademark of Philips. So Philips developed this one. So two-wire interface is open implementation used by Atmel and others. So what is the advantage? Why people developed this? Because we got SPI, then we got UART, then why Philips thought of I2C? Because Philips thought of I2C because SPI, when you have SPI, what you are doing is you are having a three-wire, then you got select. But then that is a bit complicated. When you connect more, you have difficulty because number of pins will run out in your device. Then the advantage of I2C, then that made people to think. So that's the reason that I also want to teach you the thinking part. Then people thought, why can't we connect these slaves? Because you got previously you got a master. So previously in the SPI, so why Philips developed this one? Previously this is your master or this is your microcontroller. Then master is connecting three wire, that is the slave 1, SL1. Then again this 3 to, so this 3 to another SL2, slave 2, and then another slave 3. Then you got select. You can select this one, or you can select this one, you can select this one. So then you need a lot of pins and you will run out of pins. Then Philips thought, why do we need these many pins? Can we connect these things in parallel? Slave 1, slave 2, slave 3, and then all connect to one line. And then why can't we use one master here? And then all connect, same line. Why can't we share the same line? Because that's a good way of thinking. But then when you share the same line, what will be the problem? Yeah. So that's the reason I2C need an address. So now you know why I2C need an address. Because these are some fundamental things people might ask you. Why do you need address for I2C? Why address clash is happening? So that's the reason when you are interfacing 10 sensors, each sensor should have a different address. If you don't have different address, what will you do? So you have to use a mux. You can mux it so that you can, using mux, you can select one by one quickly. There are quick mux. So every slave has an address. So without address, it's difficult. Slave will only respond to the messages sent to their addresses. Removes the need for chip select lines. See, this one is avoiding chip select as well. See, this is a master, and then this is a slave. So this could be ADC, DAC, microcontroller. This is a master one. More complicated protocol than UART or SPI. Again, synchronous. Master must poll slaves to read data. 127 slaves can be connected to a single bus. See, speed up to 3.5. Sorry. Yeah, so it's a synchronous. Master must poll slaves to read the data. 127 slaves can be connected to a single bus. Speeds up to 3.4 megahertz, 5 megahertz as defined in the standards. And then maybe in some interviews, people might ask you, some companies, which protocol you will be using when you have so many sensors. Whether you will use SPI, because we asked this question when we appointed an engineer in the department, and then they answered correctly I2C. So then, since multiple devices share a single bus, an address system is used. And then I have given more details here if you want to further look into it. The master sends the requested slave device address and then a bit indicating if a read or write is required. The corresponding slave sends an ACK. An ACK sent after every byte of data. Master always controls clock. Start stop ACK and NAC defined in I2C protocol. When you do this one, it's clear. So I have given some more. Slave address and then data transferred n byte plus acknowledge. So I give a bit more details if you want to look into it. But then what you have to understand is this is a very bit more of a complex communication protocol. It only uses 2 wires, but then it can connect to so many things, so many devices if you want to interface. And then we need an address, yes.
The address is only 7 bit or 8 bit, sir?
Uh,
So you were saying 127 slaves, but
Yep.
if you have 8 bit, you can have 255 addresses, sir.
No. Because you got 2 lines, 2 wires. So I2C example. So I2C example is suppose you are developing a plant health monitor. Want devices to be solar powered. So low power microcontroller, maybe this is a tiny 85 is a low power microcontroller used. And then this, when you use this microcontroller, it has only 6 I/O pins. So SPI can't be used because you are going to make a weather station. You are going to monitor the so many plants, plant 1, plant 2, plant 3, and then each plant 1 you got a soil moisture sensor, light sensor. Plant 2 you got a soil moisture sensor, light sensor. Plant 3 you got a soil moisture sensor, light sensor. And then when you are using these things, then when you are using microcontroller, if your microcontroller has only 6 I/O pins, then how can you connect 6 I/O pins to so many sensors? You know what I meant? Then you have to think of, yes, then since it would require 9 pins, 3 SPI plus 6 CS, because in the I/O pins you have to allocate for the 3 SPI, then you need the select pins. Then you can't use your SPI. Then I2C allows for the required 6 sensors to be connected using only 2 pins. See? So you have to check, if your microcontroller got so many pins, yes, maybe you can use SPI, but that is not practical. So that is a limitation. When you have the pin, I/O pins are limited, then that's the reason when you want to interface with so many devices, you need to use I2C. So summary. So wires, number of devices, modes, maximum speed uses. So this one is useful for you maybe in future as well. Wires, SPI 3 plus CS for every device. UART 2, I2C 2. Number of devices limited by available CS pins. So that's the problem. 2 point-to-point device. I2C 127. Mode, this is synchronous because clock. Here asynchronous, no clock. Synchronous. Maximum speed limited by devices, more than 100 megahertz possible. Usually 20 kilobits per second maximum. 2 megabits per second is possible these days. I2C 3.4 megahertz or 5 megahertz as defined in standards. Uses used for high speed data transfer with devices like LCD screen because you need to update the screen quickly, or when a small number of devices are needed. Then UART used when asynchronous operation is decided, such as control interfaces. You don't need to be synchronous. I2C used when a large number of devices are needed. Example, distributed sensor networks and LED strips. So that's the reason I2C required. So these are the summary of communication protocols, so that you got an idea of all these communication protocols, because you should be knowing when to use, and so that because this one I developed based on my own experience dealing with some of you, and means some of the questions, these are the things you should be knowing when you design a system. Otherwise you will be wasting some time in designing in some way, then you will have issue, then you will sort it out. So that's the reason I included. This is again non-examinable. So then I got 2 more lectures on Friday. I have booked from I think 12 to 2. So that is again non-examinable, non-compulsory, because that is not in the part of the timetable. So what I am planning to do is I will be covering some thermal stuff. How will you find out the temperature in the PCB? What will happen when you have high currents, something like, again non-examinable. Plus I will be discussing some past exams, because ESD means a bit different compared to your ECD exam. ECD exam, everything is from the syllabus, but then the ESD, obviously we will ask questions from the lecture slides, but then we will be also asking system level questions, whether you know the system level concepts. Like when you say that you design some devices, then we will give you some requirement. Can you draw the block level diagram? Can you draw circuit inside? Something like that. So that I will go through some of the past questions and some example questions, so that you will be better prepared for the final exam. So I'll see you on Friday, and then I also will post the dates for the extra lab sessions. Yeah, so I got your email.
Oh,
Yeah. So the last year I delayed your email because I had to talk to David Watson. Whether
I got my components. I finished assembling my circuit board, so now I assume I need to use JTAG to be able to burn the bootloader onto it.
But then did you source your components or
Some of them, yeah.
yeah, because from the last year actually we don't have, I think, the components. I think you emailed me about the components.
I was missing an 80 mega.
No, but then you got the
Yeah. Anyway, so my board's finished. I now need to flash the bootloader, but I don't have a JTAG programmer. I asked in my lab and they said they didn't know what was going on, how I start to program it. So how do I take the next step?
So you already this week there is a discussing area that part. When is your lab?
Friday.
Right, okay, I got the time.
Yeah. So I'll just wait till Friday.
Friday. So you came up here from again I'm following us. So you came, you want to program the microcontroller.
Yeah. So I'm up to the stage.
Yeah, I think the programmer will be getting this week and then so it should be fine.
We just feel like this is the floor. This is the demonstration. Ask questions. And then especially straight off.
我他妈那个羡慕呀，想看我。没有人认识吗？对。可能就是大的。我靠，那我凉了。我要三个，我要四个。哇，别现在怎么从不了？自然还大了，我们大。大了，因为我知道今天晚上。